Welcome everyone. Welcome to this presentation on irrotational flows. I'm Dr. David Nagaratnam presenting this lecture on irrotational flows. Earlier we learnt about Gauss divergence theorem and time derivative of an integral, and we learned about the derivation of mass conservation equation and continuity equation in fluid mechanics. And then we learnt about the incompressibility condition in fluid mechanics, which says that the divergence of the velocity vector has to be equal to 0. Today in this lecture we'll be learning about the flow at a wall angle, and then we'll be learning about the potential flows called the sources in the sink, and then the irrotational vortex doublet and the flow past a half body, flow past a circular cylinder, and also about the Blasius theorem. Essentially, we learned that the condition of the incompressibility for an irrotational constant density flow has to be, it will be represented by the divergence of the velocity vector being equal to 0. Under such a scenario, the momentum equation reduces to the form as shown here. Essentially, there is a balance between the pressure gradient and the total derivative of the velocity field. Now, a viscous flow past a streamlined body is shown here in the schematic. Essentially, there will be a boundary layer, a thin region where there will be sharp gradients in the velocity profile, and then there will be an outer outer irrotational region. It is this very thin region very close to the body where there is a viscous boundary layer and the velocity, there will be sharp velocity gradients. The streamlines in the flow past this streamline profile is shown here in the schematic. Now, such a two-dimensional incompressible potential flow is represented by a continuity equation which says that the divergence of the velocity vector has to be 0. For the case of a two-dimensional flow, we have this particular functional form of the continuity equation as shown here. It says that the divergence of the velocity vector is equal to 0, that is dou u by dou x plus dou v by dou y is equal to 0. Now, the condition of irrotationality for such a two-dimensional incompressible flow, which is called a potential flow, is going to be given by this particular functional form, which says that the curl of the velocity vector is equal to 0. The velocity vector being represented by two components, u and v. U is given by partial derivative of psi with respect to y, and v is given by the negative of the partial derivative of psi with respect to x. And hence, in such a case, the condition of irrotationality becomes of the functional form as shown here, dou v by dou x minus dou u by dou y is equal to 0. The velocity component in the horizontal direction is represented by dou phi by dou x is dou x, and the velocity component in the vertical direction is represented by dou phi by dou y. Now, the Cauchy-Riemann conditions hence become based on the derivatives with which we represented the component of the velocity in the horizontal direction becomes of the form as shown here. Essentially, these are relating the velocity component in the horizontal direction and the velocity component in the vertical direction with the gradients of phi and the gradients of psi. Now, the streamlines and the equipotential lines are perpendicular to each other in a potential flow, and hence in such a scenario, gradient of psi and gradient of phi are perpendicular to each other. Gradient of phi is represented by this particular vector form in 2 dimensions, and the gradient of psi is represented by this particular form. And hence, in such a scenario, we have the product of dou phi by dou x and dou psi by dou y. Here dou phi by dou x is u and dou phi by dou dou psi by dou x is v. Similarly, dou phi by dou y is v, and dou psi by dou y is minus u. And hence we have the lines of constant potential function and the lines of constant psi are perpendicular to each other. Now it is to be noted that phi and psi individually they satisfy Laplace equations, and hence del squared phi is equal to 0 and del squared psi is equal to 0. Now the conditions that the potential flow has to satisfy is that it satisfies the no normal boundary condition at the boundary of a body. Say for example, phi is a constant perpendicular to the surface of the body, and the body itself, which we are studying the potential flow. The body itself can be represented by a stream function, which means that dou psi by dou s is equal to 0. And the condition at the infinity is that the flow being irrotational in a region well past the surface of the body, dou psi by dou x is equal to u and dou psi by dou y is equal to u. The flow has to satisfy the Bernoulli's condition, Bernoulli's equation, which says that the sum of the pressure and the dynamic pressure is a constant. Essentially, the approach will be that is used in order to study such a potential flow is complex variable analysis. The complex variable which we will be using is z. Z is x plus iy. It can also be represented in polar coordinates as r e to the power I theta. The complex potential W is phi plus I psi, where phi is the potential function and psi is the stream function. Now, taking the derivative of W with respect to z, we have u minus iv. This can also be represented in complex notation as q e to the power minus a alpha, where alpha is the orientation of u and v components, and q is the magnitude. Magnitude in this particular case, it is equal to square root of u squared plus v squared. Now let's consider a particular flow, that is the flow at a wall angle. Here W is a z to the power n. Z is the complex number represented by r e to the power I theta. In this particular case, upon expanding, we have a r to the power of n cos n theta plus I sin n theta. Here W we said that it is equal to phi plus I psi. Here phi is a r to the power n cos theta, and psi is a r to the power n sin theta. Now upon differentiating W with respect to z, we have n a z to the power n minus 1. Now upon substituting n to be equal to pi by alpha, we have this particular functional form for the flow at a wall angle. Now for several values of, now n can take several possible values. Depending on the value of n, we have several flow scenarios as shown here. When n is equal to 3, we have the flow very close to a sharp edge, whereas n is equal to 2 represents the flow past perpendicular when that is the angle being equal to pi by 2. When n is greater than 3, we have such a flow scenario. We have this kind of a flow pattern. Now when n becomes lesser than 1, that is in this particular case n is equal to 4 by 5, we have a flow past an expanding edge or an expanding corner. Whereas when n is equal to 1 by 2, we have such a flow past a flat plate like scenario. Now let's consider the potential flow, namely the source and the sink. In such a scenario, the potential function is represented by m over 2 pi natural logarithm of z. Now, under such a scenario, the stream potential function is represented by m by 2 pi logarithm of r, and the stream function is represented by m by 2 pi theta. The radial velocity component then becomes of the form shown here. Upon differentiating this phi partially with respect to r, we get m by 2 pi r. Now upon differentiating phi with respect to theta, because there is no dependence on theta, u theta becomes equal to 0. Now if this source is positioned at a point z is equal to a, then the complex potential becomes of the functional form shown here. The streamlines which are emanating from the source is given by psi is equal to constant line. The constant potential lines are shown by phi is equal to constant lines. Now let's consider an irrotational vortex which is represented by the complex potential as shown here. Here z is equal to r e to the power I theta. Phi in such a scenario becomes of the form as shown here, and psi becomes of the form as shown here. In the case of an irrotational vortex, ur is equal to 0. We can clearly see that upon differentiating phi partially with respect to r, ur is 0. Upon differentiating phi partially with respect to theta, and we have u theta being represented by 1 by r times dou phi by dou theta, and such a scenario u theta becomes of the form shown here. There is only an azimuthal component of the velocity, whereas the radial component of the velocity for the case of an irrotational vortex is equal to 0. Now let's consider a potential flow called a doublet flow. A doublet flow is formed by bringing two source and a sink, which are set apart from each other by 2 epsilon, where epsilon is a very small parameter. Under such a scenario, a source which is apart from which is placed at a distance epsilon from the origin can be represented by logarithm of z plus epsilon, whereas a sink which is positioned at x is equal to epsilon can be represented by this particular potential function. Now this can be written compacted in this particular form. Now upon doing a series expansion of this particular term, we have m epsilon over pi z. Now this is the stream functions, that is these are lines of constant psi for a doublet or a dipole. Essentially the potential function for a doublet or a dipole is going to be mu over z, where z is r e to the power I theta. Now upon differentiating w, w is essentially phi plus I psi. We have phi, that is the potential function represented by this form, and the stream function is represented by this particular form. Now we may choose to write psi, and we may choose to expand psi, and we'll get this particular form for the streamlines. Now let's consider the flow past a half body. Well, a half body is formed by a combination of a source and a uniform flow. The uniform flow is represented by uz, and the source is represented by m by 2 pi ln of z. Under such a scenario, the stream function becomes of the form as shown here, by essentially this is written in polar coordinates, where z is equal to r e to the power I theta. Under such a scenario, w is essentially phi plus I psi. The stream function then becomes of the form as shown here. Now, at the stagnation point is observed at a distance say a from the origin and positioned at the azimuthal location of theta being equal to pi. Under such a scenario, ur is essentially going to be represented by dou psi by dou theta being equal to 0. Under such a scenario, we have at a at the point a comma pi, we have ur being equal to 0, and hence we deduce the value of a to be of the form as shown here within the box. The value of the stream function at this which is passing through the stagnation point is represented by this particular equation. The equation of the streamline then becomes of the form as shown here, which passes through the stagnation point is shown by this particular form. Here theta is the azimuthal position. Essentially, this is the streamline pattern for the flow past a half body. Psi is equal to m by 2 is the streamline which is far away from the stagnation point. The stagnation point here is represented by S. The dividing streamline is represented by psi is equal to m by 2. The dividing streamline divides the flow that is away from the half body and the flow that is due to a source kind of a flow. The flow due to a source is bound within the line psi is equal to m by 2. The flow due to the uniform stream is divided by this particular psi is equal to m by 2 line. Now, the half body width is represented by r sine theta, which is going to be equal to of the functional form shown here. It can be essentially deduced from the equation of the streamline that is passing through a stagnation point. Now, from Bernoulli's equation, we know that P plus half rho V squared is equal to P infinity plus half rho U squared, where P infinity is the pressure at a point which is further away from the body. The velocity of the free stream is represented by capital U. Here, capital U is the velocity due to the source due to the free stream. And hence, in such a scenario, the non-dimensional pressure or the pressure coefficient can be represented by the functional form as shown here. Now, let's consider the flow past a circular cylinder without circulation. Essentially, it's going to be a combination of a free stream or a uniform flow and a doublet flow. Under such a scenario, using which is represented by in r theta in polar coordinates or r theta coordinates, we deduce this potential function and stream function to be of the form as shown here. Now, upon differentiating phi partially with respect to r, we get the radial velocity, and then differentiating phi partially with respect to theta, we get the azimuthal velocity of the form as shown here. Now, for such a flow past a circular cylinder without circulation, we have the flow velocity, the azimuthal velocity at r is equal to a being given by this particular functional form. Now, the distribution of pressure at various azimuthal positions on the surface of the cylinder can be shown to be of the form as shown here, which is essentially of the form of 1 minus 4 sine squared theta. Now, upon comparing the distribution of the pressure coefficient at various azimuthal positions against a real flow situation is shown here in this particular graph. Essentially, for a real or a viscous flow, there is a drop in the pressure. Because of the weight that is present in a viscous flow, whereas in inviscid flow we do not have such a feature, which results in a larger magnitude of non-dimensional pressure. Now, let's consider the flow past a circular cylinder with circulation. Under such a scenario, the flow can be modeled by an uniform flow, and then we have a doublet flow, and then we have vortex flow, which is represented by the velocity potential as shown here. Essentially, we have the which can be expanded by writing z in terms of polar coordinates. That is, z is essentially r e to the power I theta, and hence we have the stream function being represented by this particular form. Now the azimuthal velocity is represented by minus dou phi by dou r. Upon differentiating psi partially with respect to r, we have this particular functional form for azimuthal velocity. At the surface of the cylinder, that is at r is equal to a, the azimuthal velocity is represented by this particular functional form. Now, this azimuthal velocity is equal to 0 at certain azimuthal positions, which can be found by equating u theta to be equal to 0, which is going to be sine inverse of negative of circulation over 4 pi au. Here a is the diameter of the cylinder and u is the free stream velocity, and gamma is the circulation that is introduced due to the presence of vortex. Now, the pressure distribution on the surface of the circular cylinder with circulation can be deduced from Bernoulli's equation, which says that P plus half rho V square is going to be equal to P infinity plus half rho capital U square. Under such a scenario, upon the pressure at R is equal to A is going to be represented by this particular functional form. Now, let's consider, in order to find the force that is exerted on the surface of the cylinder, let's consider in such a two-dimensional cylinder where P is the pressure that is exerted on the surface of the cylinder, which is positioned at theta in the azimuthal direction. The radius of the circular cylinder is A. Under such a scenario, the lift force is going to be the pressure times sine theta. Pressure times sine theta is going to represent the component of pressure in the y direction times A d theta. Now, upon integrating this from 0 to 2 pi, we will get the component of force due to the pressure that is exerted on the circular cylinder. Now, such a lift force is the force in the y direction is going to be represented by rho u kappa. Here, kappa is the circulation that is introduced due to the presence of the vortex. Now, let's consider the derivation of force that is exerted on an arbitrary two-dimensional body in a potential flow. Here, the arbitrary two-dimensional body is going to be represented by this particular form. Here, theta is the position of the an arbitrary element of the two-dimensional body. The vertical force is going to be P dx, and the horizontal force in such a scenario is P dy, where P is the pressure that is exerted on the element that is inclined at an angle theta with respect to the horizontal. Under such a scenario, the horizontal force, which is here represented by drag force, which is going to be called the drag force, and the vertical force, which is going to be called the lift force, is going to be given by minus P dy and P dx. Now, this can be represented in complex notation as minus I P dz, essentially dz star. Dz star is the complex conjugate of the complex variable dz. Now, upon integrating both sides of the equation, we will have d minus il being given by minus I closed integral of p dz star. Here, essentially, how we can find the pressure that is from Bernoulli's equation, which states that P infinity plus half rho u square is going to be equal to p plus half rho u squared. U is essentially going to be velocity on the surface of the body. Now u can be represented by u square plus v square, which can be written in complex notation as u plus iv times u minus iv. Now upon expanding, we have, upon writing it in terms of the Bernoulli's equation, we have this particular functional form. Now essentially u plus iv can be represented as as a product of its magnitude and exponential of I theta. Now u plus iv, u square root of u square plus v squared is the magnitude of u plus iv, and theta is the position of the element which is oriented at an angle theta with respect to the horizontal. Now dz, the element dz has a magnitude modulus of dz, and theta is the orientation of the element which we are interested in. Now essentially it is to be noted that u minus iv dz star is real value, and it can be shown that u plus iv times dz star is going to be equal to u minus iv dz. Now based on that observation, it can be shown that d minus iz is going to be represented by I times rho by 2 closed integral of the derivative dw by dz whole square times dz. Essentially this particular term dw by dz is u minus iv. Now let's now for the case of flow past a circular cylinder with rotation, we learned that it can be represented by sum of a free stream or a uniform flow, which is represented by complex potential given by uz, and doublet flow, which is going to be represented by the complex potential of the form shown here, and the doublet flow is going to be represented by the form as shown here, whereas there is a vertical flow which is going to be represented by the form I gamma by 2 pi ln of z. In such a scenario, we learned that sum of residues is going to be closed integral of f of z dz is essentially going to be 2 pi times sum of residues. And in such a scenario, we observe that the drag force for the case of a flow past a circular cylinder with rotation is going to be equal to 0, whereas the lift force is going to be represented by rho u gamma, where gamma is the circulation due to the circulation of the cylinder with rotation. Now essentially what we have learnt here is we learnt about several flows, such as several potential flows, such as the flow past wall angle sources and sink, and irrotational vortex, and then doublet flow, and the flow past a half body, and flow past a circular cylinder. And I believe you were benefited by this. I thank you for giving this opportunity to make a small talk.